This is geometry lesson 5.5 and 5.7. So we're going to start in 5.5 and then we'll jump into 5.7. So just real quick here, one little point I want to get to in 5.5 and then we'll spend most of our time in 5.7. So 5.5 is all about proofs using reflections. The big idea says when you know that certain points are the reflection images of other ones, you can use the definition and preservation properties of a reflection to deduce, which means to conclude many things about those points. So we're going to look at the perpendicular bisector theorem. If you take a look at the picture, it says that MP, this line right here, is the perpendicular bisector of TC. We've been drawing perpendicular bisectors. We know what those are. They hit at 90 degrees, and they cut this into two equal pieces. So TM is going to equal MC because this is the bisector of TC. It's cutting it perfectly in half. We'll get to this part in a second. What I want to look at, though, is the fact that we are going to consider this a reflection across line MP. The reason we can do that is because when we reflect something, like let's say reflecting point T across that line, it ends up the same distance on the other side, which is what we have, and the line connecting the pre-image and the image has to go through the line of reflection at 90 degrees, and that is what we have. So while this is a perpendicular bisector of this segment, we can also look at it as a reflection across this line. So if I reflected point T across line PM, where would I end up? So T, the same distance on the other side, 90 degrees to the reflection line, and we're going to end up at C. Okay, and then the opposite would be true as well. If I reflect C over PM, I'm going to end up at T. So reflection over PM of C is going to put me at T. Now I can also consider P in this scenario. If I reflect P over that line, well, point P is on the line, so that reflection will remain right where it's at. So P is not going anywhere. So why would I even consider that? Because we're going to be looking at the full segment, PT, and then over here, PC. And so can these be considered a reflection across that line? And the answer is yes, because T gets reflected across, P gets reflected across, but it's on its same side. And what do we know about reflections? We know that distance is preserved. So the distance between T and P, when I reflect them to the other side, will remain the same. The distance between them is preserved in a reflection. So I'm going to write another one here. If I reflected over PM, the whole line PT, I end up with PC. Let's try and keep these separate here. And vice versa, if I reflected PC, over that I end up at PT, which means those are equal to each other. I can say PT equals PC. And why is that? Let's write it down so if we look back, we know. Reflections preserve distance. So to answer this question, if PT is 10, I know that PC is also 10. So let's take a look. The perpendicular bisector theorem says if a point is on the perpendicular bisector, like point P is on the perpendicular bisector, then it is equidistant from the endpoints of the segment. So the endpoints of the segment are T and C. Any point that's on this line, perpendicular bisector, is going to be the same distance from C as it is from T. And that works for P as well. P is on the perpendicular bisector. It's the same distance from T as it is from C. That's what the perpendicular bisector theorem says. And that would be true again anywhere on this line. All right, that's the main thing I wanted to cover in 5.5. So let's jump into 5.7 now. We're going to be looking at the sums of angle measures in polygons. So the big idea sounds a little complicated, and we'll break it down for you. So it says the sum of the measures of the interior angles of a convex, we know what that means, polygon, is determined by the minimum number of triangular regions into which the polygonal region can be divided. Okay, so that just sounds like a big mess. So basically, if we have a polygon, a shape, we can cut that shape into triangles, and we know that the angles of a triangle add up to 180. And so we can use that 180 degrees that are inside all these triangles total to help us find the total degrees in this bigger shape. So basically, we're cutting these polygons into triangles so that we can discover how many degrees total are on the inside. But we're going to skip the discovery phase and jump straight to the formula that works. Okay, so the polygon sum theorem says the sum means you're adding. So if you add everything up, the sum of the measures of the angles of a convex. So first of all, remember a non-convex would look like this, right? I can go from one point to another point and I leave the region. That's non-convex. Just reminding you of that. We went over that earlier in the book. So we're only talking about convex polygons. N just represents how many sides. So a pentagon, right, would be 5. We have octagons and nonagons and decagons. N is just representing how many sides we have. And so here's the formula. It's the number of sides. So octagon, we would put 8 minus 2, and then we're going to multiply by 180, and that tells us the total number of degrees in the shape. So let's think about a triangle for a second. We already know that these add up to 180. We've talked about that before. So let's see if this works for a triangle. Triangle has 3 sides, so we put 3 in for n. 3 minus 2 is 1, so 1 times 180 equals 180. So of course a triangle has 180 degrees when you add up the interior angles. That answers our first question here. What's the sum of the interior angles of a triangle? 180. So this angle plus this angle plus this angle has to add up to 180 in every single triangle. So what about a quadrilateral? 4-sided shape. Let's use the formula. You put 4 in for n. So it's 4 minus 2 times 180. So 4 minus 2 is 2 times 180. It's 360 degrees. Okay, so that means if I add up the interior angles of any 4-sided shape, I have to get 360 degrees. Let's see if that makes sense. If I take a rectangle, I know every single angle is 90 degrees. That's what makes it a rectangle. 90 plus 90 plus 90 plus 90, sure enough, that's 360. But what this is saying is every 4-sided shape will be 360. Doesn't have to be a rectangle. It can look like this, or maybe this is 90 and this is 90, but these are not 90. Doesn't matter. 4 sides, 360 degrees total. Okay, so what about an octagon? 8 minus 2 times 180. So number of sides minus 2 times 180, and that comes out to 1080 degrees. Okay, so you just take the number of sides minus 2 times 180, and that will give you the total degrees on the interior of a convex polygon. All right, we'll come back to that. Now we're going to look at exterior angles of polygons. So obviously exterior means on the outside, but this is very specific, not just any angle that happens to be outside of the shape. So an angle is an exterior if and only if it forms a linear pair with one of the angles of the polygon. So when they say one of the angles of the polygon, they're talking about the interior angles. So to be considered the exterior angle has to form a linear pair with one of the ones on the inside. Here's how it works. I like my own definition better. Definition of an exterior angle is the extension of a side. So notice I just extended that side, and it's the angle formed by that extension and the other side. So that angle right there would be considered an exterior angle. It's the extension of a side, and it's being measured with another side. So the reason I say another side is because if I extended this side and then tried to look at the angle it forms with itself, that's always going to be 180. So that's not what we're looking for. We're looking for, here's the 180 I'm talking about. We're not looking for that. That's going to happen every time we extend the side. So we're looking for the angle that that extension forms with this other side. So if you bring that down to this picture, 1 and 2 are both exterior angles. So this would be like angle 1. Angle 2 comes from the extension of this side, right? And then we're looking at the angle that that forms with the other side it's attached to. So that's angle 2. Both of those would be exterior angles. They are linear pairs with this angle, both of them. Linear pair, this is a linear pair. And then if you look at y right here, y is going to be vertical with the interior angle if we come up with two extensions there. So if we have two exterior angles from the same spot, we create this nice little vertical spot. Whatever the interior angle is, this will obviously equal it because vertical angles are equal. All right, so let's use this information to fill out this figure that we've got right here and then discover some things here as we move forward. Okay, so in this figure, you're giving two angles. It says that there are four angles missing. So one of them here on the inside, and then the three exterior angles. We've got the extension of these sides creating an angle on the outside. Those are linear pairs, right? We've got this 116. It's a linear pair with this angle right here. So all I have to do is 180 minus 116, which is 64, and I've got this angle of 64. So I can do 180 minus 22, that's 158. So this angle out here is 158. Now, over here, I first need to find this third side. Remember that third side, together with these two that you have to add up to 180. A triangle adds up to 180, the interior angles. So I'm going to do 180 minus 22 minus 116. That gets me 42, so this angle in here is 42. And once I know that's 42, it's a linear pair with this exterior angle, so 180 minus 42 is 138, so this is 138. All right. On the next page, we're going to be looking at some more theorems specific to these exterior angles, and I want to discover them before we flip over and actually talk about it. So if you take a look at this angle, 158, and then you look at these two angles that are not the linear pair of it, 116 plus 142, I'm sorry, 116 plus 42 equals 158. Okay, that's not happenstance. That's going to happen every single time. So I've got this 64. If I look at the two angles, interior angles, that are not the linear pair to it, 42 and 22, add those together, 42 plus 22, you get 64. The same thing would be true for the 138. Okay, I'll put a star to make it different. Take the two angles that are not the linear pair to that angle. 116 plus 22 is 138. Okay, so we're discovering that the exterior angle is always equal to the sum of the other two angles that are not the linear pair to it. All right, that's always going to be true, and we'll talk about that more on the other side. We're also going to want to look at these exterior angles added up all together. So if I add 158 plus 138 plus 64, it's 360 degrees. Okay, so the exterior angles of a triangle is 360 degrees. We will come back to that and see how that affects the shapes when we have more than just three sides. Because right now, if we're just looking at triangles, we know the inside's 180 and the outside's 360. So maybe that's related, maybe it's not. We're going to have to look at some other shapes to determine whether that's always true or there's a correlation between how many degrees are on the inside and the outside. All right, so let's take a look at the back. Here's the theorem that we discovered. In a triangle, the measure of an exterior angle is equal to the sum of the measures of the interior angles at the other two vertices. So those are the ones that are not the linear pair. So for the one that's given, the measure of angle 1 is equal to 5 plus 6. You have 1 equal to 5 plus 6. The measure of angle 2, this exterior, is going to be equal to the other two interior angles added together, 4 and 6. And then 3, this one out here, is going to be the addition of 5 and 4. So that's what that theorem is. We discovered that on the last one. Okay, So let's now use all of that information to solve a couple problems and maybe make even one more discovery along the way. So the figure at the right is a pentagon, 5 sides, and the measures of 4 interior angles are given, and then you can see we've got exterior angles as well. So we're going to follow those 3 steps and see what we find out. Number 1, find the measure of the 5th interior angle. So we're just missing one, but we can figure out what they all have to add up to and then figure out what we're missing. So remember, the formula is n minus 2 times 180 to find the total number of degrees on the inside here. So if we have 5 sides, it's 5 minus 2 times 180, which is 3 times 180, which is 540. So a pentagon has 540 degrees on the inside. So I'm going to subtract these all away from 540 and see what I'm left with. Since there's only one angle missing, once I take these away from 540, I'll know what that missing angle is. So minus 105, minus 110, minus 106, minus 120. Take away all those angles. And of course, you could add those up first and then subtract them from 540. And that's going to leave me with 99 degrees. So I know my last angle is 99. So I use this formula to find out the total degrees in this and then just subtract away what I've got to find that last one. So step 2 now, find the measure of each exterior angle. So for these, we know they're all linear pairs. These have to add up to 180. So 180 minus 99 means this angle is 81. Again, linear pair. Right here, adding up to 180, 180 minus 105 is 75. Add these together to get to 180. 110 plus 70 is 180. 106 plus 74 is 180. And 60 and 120 is 180 degrees. So there's the measure of all the exterior angles. Let's go ahead and find the sum now. So if we add up all the exterior angles, 75 plus 70 plus 74 plus 60 plus 81, if you add all those up, you get 360 degrees. Hey, that's the same number we got for the triangle, 360 degrees. And so we're discovering that the number of sides actually does not affect the exterior angles in terms of the total sum. It certainly affects the interior. It's going to be different for every single polygon depending on how many sides it has. But we just discovered that the exterior does not change. Now, here's why. First of all, here's the theorem. The sum of the measures of the exterior angles of any convex polygon is 360. Always 360. So it doesn't matter how many sides it has. Okay, those angles are still going to add up to 360. If I extended these sides here for a second, I'm going to demonstrate why this works. And then I draw a circle around this. Right, we know a circle is 360 degrees total. Okay, so this part of the circle is 74, this part of the circle is 60, this part is 81, this part is 75, and this part is 70. Full 360. Same thing could be said over here. Extend those sides out a little bit. Okay, if I've got a circle, I know that's not a perfect circle, but this portion of the circle is 138, 64, okay, and 158. And so that makes your full 360, if that helps you remember it. So your exterior angles are going to be 360 no matter what. All right, so we've kind of discovered 2 pretty cool things that we can just plug in the number of sides into this formula and figure out the total number of degrees inside a polygon. And now we know that 360 degrees would be the measure of all the exterior angles added up to any size polygon. So let's go to example number 2 and kind of finish this off now. We're going to describe how to calculate the measure of one interior angle in a decagon, that's 10 sides, you can count them up, whose angles are all congruent. So this is called a regular polygon, or a regular, in this case, decagon. When you see the word regular, it means all the angles, all the sides are congruent. 10 equal sides, 10 equal angles. So we're going to solve this two different ways. I'm going to show you that you can use either the exterior angle theorem or the interior angle theorem to still get the same answer for this question. So let's start with the polygon sum theorem. So if we have 10 sides, plug in 10. So 10 minus 2 is 8 times 180. That's 1440. So the total number of degrees in this is 1440. And since they're all exactly the same and there's 10 of them, I can just take 1440 and divide it by 10. And that means each one is 144 degrees all the way around. If you added those up, you'd get to 1440. Perfect. The other way you could do this is look at this exterior. We know that the whole thing is 360. Every shape is 360. And if I extended an exterior on every single one of these, there's 10 sides. I would have 10 of them. And they're all going to be equal to each other, okay, because it's a regular polygon. All of these are congruent. So 360 degrees total split into 10 different angles means they're all 36 degrees. So each one of these exterior angles would be 36. Now remember, that's not true for all polygons, that they're all equal. We just looked at one that wasn't, right? But if all the interior angles are the same, all the sides are the same, all the exterior angles will be the same as well. And again, these are linear pairs to what's on the inside. So this angle here plus the 36 has to equal 180. So I can do 180 minus 36. I get 144. And so now I know all of these angles are 144. So two different ways to get to the same answer.